Good morning, everybody. Today I will continue talking about finite dependence, but in the context not of estimating dynamic discrete choice models, but in the context of solving algorithm for solving this model. I'm going to show you that we use the concept of finite dependence to define an operator. I'm going to call it the Euler operator, and I will explain later why I call it that way. And it can be used to solve for the solution of the dynamic programming problem. And I will show you that this has substantial advantages over standard methods like value function iteration and policy function iteration. Okay? Then we have seen today and yesterday very nice methods for estimating the structural parameters of dynamic discrete choice models that do not require solving for the dynamic programming problem even once. These broadly speaking, CCP methods. And of course, there is a lot of value in that, and they are super helpful, as Bob has clearly motivated. Now, still, we can be interested in the solution of these type of models and in using efficient algorithms, computationally efficient algorithms for the solution of dynamic programming problems. At least for two reasons. The first reason is that that we use structural models to answer counterfactual questions. The main power of structural models is being able to use our model to construct counterfactual scenarios. What if the world were different according to some changes in the structural parameters, or what if the world is different according to some policies that have never been implemented, but that in principle could be implemented. Okay? And to implement this type of counterfactual experiments, we need to solve in one way or the other our dynamic programming problem. And in some cases, we have to solve it many times if we want to consider a rich set of counterfactuals. Okay? The other reason why we may want to have good algorithms for solving dynamic programming problems in this context is that we may want to use full solution methods, such as the nested fixed point algorithm or the nested pseudo likelihood estimation that I will describe in my next lecture. These methods require the solution of the involve or the incorporate an algorithm for the solution of the dynamic programming problem. In the nested fixed point algorithm, we have to do it many times. In the nested pseudo likelihood, we need to solve the model only once, okay? But still, we need an efficient algorithm for solving this type of thing, okay? This computational burden of solving dynamic programming problems, of course, is subject, as it's well known, to a course of dimensionality. The cost of solving dynamic programming problems increases exponentially with the dimension of the state space, and it can become very costly even for let me say, modest type of state space, okay? The problem is even more serious when we are talking about dynamic games, because for the solution of one equilibrium of the dynamic game, we will need to solve many times for the single agent dynamic best response. Basically, the best response function of each player involves the solution of a dynamic programming. Okay. Then in that context, we also we are in more need, let me say, of computationally efficient algorithm for solution. Okay. Then which are the standard, almost the universal type of solution method that are used for the solution of dynamic programming problems? Well, value function iteration that we have seen yesterday, Bertel talked about it. is very common. Policy function iteration, that is also called Newton-Kantorovich, and Bertel also described it yesterday, is quite common. And of course, as Bertel mentioned yesterday as well, hybrid combinations of value function iteration and policy function. Basically, these are the methods that are typically used for the solution of this. Okay? Then in this context, I'm going to consider models that have a finite dependence property. And based on this property, I'm going to define an operator that I will call it the Euler equations operator. These conditions, this operator, or these conditions, Euler equations, let me say that I'm going to define, they are always necessary conditions for these problems, but in the type of models that I'm going to describe, they are necessary and sufficient conditions to describe the solution, the full solution of the dynamic programming problem. Okay. Something that is interesting is that by using the finite dependence property, this representation of these Euler equations do not involve computing present value. Okay, they only require basically the evaluation of this Euler equation operator only requires obtaining next period expected values of utilities or payout. Okay? And then based on this operator, I'm going to define an algorithm that is basically fixed point iteration in this Euler equation iterator. And I will show that this has implies computational gains compared to value function iteration and policy function. In particular, a single iteration has the same cost as value function iteration, because basically a single iteration as value function iteration involves only obtain expected values next period, not calculating any present value of all your expected and discounted payoff for infinite period or for capital T period, okay, which is substantially more costly. And this Euler equation operator, basically one iteration has as little cost as value function iteration. What I will discuss later is that what is the problem of value function iteration that Bertel described very clearly yesterday is that it has linear convergence. It converges very slowly. Okay? As I will show later, the contraction properties of this Euler operator implies is much stronger than the contraction properties of the value function. Then it converges close to quadratic. Okay? Then the combination of these two features is going to make this Euler operator computationally more efficient, both than value function iteration and policy function iteration, and of course, any linear combination, if you want, of value function iteration and Euler equation and policy function iteration on Newton-Kantorovich, which is this hybrid method. They can be seen as linear combination. Okay. Okay, then I will start again presenting the model that you have seen already a few times. I will remind you about the value function iteration and policy function operators in this context, and then I will derive the Euler operator in this type of model. I will present the result that is it has contraction Lipschitz constant or contraction modulus smaller than beta, and then I will. I'm going to spend some time, if I have enough time, to tell you why I call this operator the Euler equation or the Euler operator is that is closely related to the Euler equations that we have with continuous choice models. And then I will present some numericals. Yeah. Questions? Okay, then let's go again with the model with a different notation. Okay, And this is then we have a Markov decision process with a discrete action. Time is discrete and indexed by t. The decision variable is a. I'm going to use a to describe the decision. This a belongs to this discrete choice set of j plus 1 choice alternative, including 0 as a possible alternative. The individual maximizes the intertemporal payoff function, that is this stream of discounted payoffs. I'm going to incorporate the decision as a subindex instead of as an argument in the function. And this pi is the per period payoff function. S is the vector of state variables that follows a control transition probability. With this transition rule, again, I'm going to use the subindex. I'm going to use the action as a subindex to represent this transition. Okay. Okay. Then this is the Bellman equation, very standard stuff. Remember, this is the Bellman equation, including all the state variables. Okay. And this is the optimal decision rule. I'm considering stationary models, and this Euler operator that I'm going to describe, the version that I'm going to present is for stationary models, and we have infinite rise. Okay, and everything is going to be stationary in this context. Okay, in this lecture. Okay. Let's see this again. The two key assumptions of, if you want the two key assumptions of in RAS model, the additive separability and the conditional independence. We consider that they are these epsilons unobservable that are additively separable. Now a small pi represents the deterministic part of the observable part of the payoff function. And then we consider that this conditional independence, that is a stronger version of the conditional independence, but this is in fact what we do in practice. I think that is consider that we have xt plus 1 here conditioning is. Okay, that's the definition of the conditional independence, but in practice, we always assume that these epsilon are independent of the x, okay? Completely, the variance and everything. And it's a bit, I find it a little bit pedantic, honestly, to consider this x t plus 1 condition. Okay. Okay, then this is, let's consider the integrated value function. Okay, the integrated value function is the value function integrated over the epsilons. Okay, and we have seen in previous lecture that we have an integrated Bellman equation that is a fixed point mapping defined in terms of this integrated value function. This is the integral of the max, of the expected value of the max, where the expectation is taken over the distribution of the epsilons. And these are the conditional choice value function. This conditional choice value function is the one period utility, or the part of the one period utility that is observable. And then next period integrated, the expected value of next period value, okay, or integrated value, okay. Then this defines, as you can see, a fixed point operator from integrated value functions into integrated value. I'm going to talk from now on about value functions without using the integrated term, but you should understand that we are working all the time with integrated value. Okay. Let me define something that is going to be useful and important for the results, and it's McFadden's social surplus function. McFadden's social surplus function applies the concept to either static or dynamic models. Basically, is give me a vector of deterministic utilities or values, V's for each possible action. Suppose that the total utility is a random utility model that incorporates also this epsilon. Then this McFadden social surplus function is a function of this vector of deterministic utilities, okay? That is obtained by as the expected value of the maximum, where the expectation is taken over the distribution. And by using this definition, and Bob has been basically use this equivalence all the time. He has been using the term, the integrated value function. He has called it the social surplus, and it is the social surplus, but it's not the social surplus, or it's not McFadden's social surplus function. I'm going to emphasize here that McFadden's social surplus function is this value as a function of the condition, the vector of conditional choice value. Okay? And this is going to be important because at some point I'm going to use derivative of this surplus function with respect to these values, and I'm going to use a theorem that is the so-called Williams-Daly-Zachary theorem. Okay? Okay, and we can we have the equivalence between these two. Okay. Okay, then in this context, what is value function iteration? It's just, well, first, what is the value function operator? It's basically in vector form, the integrated Bellman equation that we have seen before. Okay, it's basically this, the combination of this equation and this equation that give us a fixed point from values functions into value functions. We can define it in vector form by defining a vector of values for each possible value of x. Let me maintain the assumption that we have all maintained through these lectures so far until Newey's lecture, that x has discrete support. Okay. Then basically what we have is a mapping from values into values, where basically is McFadden's surplus function. What we have as an input, the vector of values, has this structure. The vector of values is the vector of payoffs for alternative A, multiplying this vector of continuation values. And we can write always the vector of continuation values as the matrix of transition probabilities, given that action A has been chosen, times the vector of value. Okay. We have this compact form of representing the whole vector of conditional choice value. Okay. Then give me a vector of values, an initial guess. I plug it in here. I obtain all these conditional choice value function. I use the expression for the surplus function, for instance, the log of the sum of the exponential if the epsilons are type 1 string values. And this gives me a new vector of conditional choice value function, and I iterate it in this way until complete. Okay? This is the value function iteration that many of you have, I'm sure that you have used before to solve dynamic programming problems, which are some nice features and some not so nice feature of this solution method. Is a contraction, as is well known. And it has modulus that is equal to B. The modulus of the Lipschitz constant of a contraction mapping tell us how fast we convert. The closer that is to 0, the faster is the convergence. Okay, the closest to 1, the slower. Okay, is the convergence. Okay. Then, because it has a Lipschitz constant that is beta, is linear convergence, and it can be very slow if beta is close to 1, okay? Thus, B is the not so good properties. This convergence is quite slow, okay? And the nice feature is that the cost of per iteration is small. And you will see later that it's quite small relative to the cost per iteration of the Newton-Kantorovich. Then it increased, the cost of each iteration increased only linearly with the number of state variables that we have in. Okay, then policy function iteration. Policy function iteration, it can be described in the space of values, as Bertel did yesterday, or it can be described in the space of choice probabilities. Today, I'm going to describe it in the space of choice probability. Then the value function iteration or Newton-Kantorovich iteration is a composed mapping. It's composed of two different mappings, okay? Or two different steps, if you want, in the evaluation of the policy iteration value. One step is the evaluation operator, and the other step is the policy improvement operator. Then what is the evaluation operator? The evaluation operator is very intuitive. Give me a vector of choice probabilities for every action and every possible state, every possible value of X. And then I can calculate what will be the present value of behaving according to these choice probabilities from now and forever in the future. Okay, that's what the evaluation operator does. Okay, give me some policy that in this case has choice probabilities, and I can calculate what is the value of behaving according to that policy. Okay. Mathematically or numerically, that involves basically solving this system of linear equation. Okay. This is the vector of values. Okay. A vector for each value of X, given an arbitrary vector of choice probabilities for every action and every step. Okay. And basically, this is element by element product. These are all vectors. These are the vector of expected values of epsilon, given that the action is optimal. In the logit case, this will be the Euler constant minus the logarithm of the probability of choosing alternative one. And this is basically the expected value next period if the vector of values is that. Okay. Then you can see that it's an implicit equation, but you can see also that we can put all that depends on, basically these are all primitive or depends on the choice probability. We can put WP here, and at the end we can calculate WP using an inverse matrix, okay? Solving a system of linear equations, okay? Of course, that is not the computationally best way of doing it, using some linear decomposition. Eigenvector decomposition is going to be numerically better, but basically is solving a system of linear equations. That's what we have to do here. Okay. Then give me a policy, give me a vector of choice probabilities. I can obtain this valuation operator by solving this system of linear equations. And then I go to the policy improvement operator. Given this W, I'm going to put it in the, let me say, logit probabilities to get what is the best response to this valuation. In some sense, I think that it's intuitive to think this as a game where an agent is playing against himself in the future. I'm going to assume that I'm going to behave in the future according to these choice probabilities. This gives me this valuation. And then given that, taking that as given, I'm going to best response today by obtaining what are the best response choice probabilities today to those beliefs about my behavior in the future, okay? That will give me a new vector of choice probabilities. And that is the policy function operator, okay? The policy improvement is trivial, okay? Especially if we have closed form expression for instance, the logit probabilities is trivial. Again, the cost increases linearly with the number of states. The main computational cost of one single iteration comes from this valuation operator. Solving this system of linear equation, the computational cost is cubic, basically, in the number of steps. Inverting matrix is cubic or close to cubic. So solving system of linear equation is between quadratic and cubic, but closer to cubic, okay? Okay, then that is what policy or Newton-Kantorovich iterations work. What are the properties? The nice property is that the contraction, the modulus of this contraction is much smaller than B. In fact, the convergence is quadratic. The convergence is quite fast, okay? What is the trade-off, or what are the not so good news about policy iteration? Then the computational cost increases cubically with the number of steps. Then eventually, if we consider basically what is the optimal algorithm when we increase the number of state variables in our model, eventually policy function iteration or value function iteration, sorry, will be better than policy function iteration, because eventually the cost of policy function will increase very, very, okay, cubically, okay, versus value function iterations that increases linear, okay? Okay, then this and combination of these basically sometimes, as Bertel described, starting with value function and eventually in the last stage doing a few policy function iterations is the way that the type of algorithm that we use to solve these models. And we use, for instance, for counterfactual or for nested fixed point or MTL. Okay. And let me now describe this other operator that we denote Euler operator. Okay. Then it's going to be a fixed point mapping in the space of value difference. Okay. Remember Bob inversion result, or Hodge-Miller inversion theorem. We can always go from value difference into choice probabilities and vice versa. This is a one-to-one mapping. Then this mapping that I'm going to describe can be described as a mapping from value difference into value difference, or also as a mapping from choice probabilities into choice probabilities. Well, it turns out that the good computational properties are when we have the mapping from value difference into value difference. When we consider the mapping from choice probabilities into choice probabilities, we have not been able to solve even that is a contraction. And we have unfortunately some examples where it is not a contraction. Okay, and I'm going to describe here this operator using value difference. Later, I will describe basically the relationship with a similar mapping, but in terms of choice probability. Okay. Then let's choose a baseline choice alternative 0, and let's define this value difference. Okay. And this V tilde is the vector of all the value difference for state X and for all the choices which are not 0. Okay. Then we know that this vector of values, okay, is equals to the social surplus defined in terms of the whole vector, but we can always basically, because this expected value of the maximum, we can basically take add and subtract the value of the choice alternative 0 from the social surplus, and we can write basically the expression in this way. Okay. Then the value of the unconditional value is equal to the value of choosing an arbitrary alternative 0, plus this description of the social surplus. But now this social surplus is not in terms of values, but in terms of value difference, in terms of all the value difference, except the value difference of choice alternative 0, that is 0. Okay. And now I'm going to do basically what Bob describes as telescoping. Not yet, but for the moment, okay, let's consider the definition of conditional choice value function. Remember that let me go back. The conditional choice value function of one particular choice alternative is today's payoff plus next period expected values, okay, given that alternative A has been chosen today. Well, the difference between this value VA and V0 will be the difference between today's payoff for alternative A minus alternative 0. And then we have this integration, okay, of this expected value. This value is the same under alternative A and alternative 0. Then what we will have here basically is the difference between the transition probabilities for alternative A minus the transition probability for alternatives. Okay, that will give us the equation for V tilde, for the value difference. Okay, and that's exactly what I have here. Okay, and this is just the value V at period t plus 1. But we know that we can write the value at period t plus 1 as the sum between the value of an arbitrary choice alternative plus the surplus function. Okay, Remember that these are payoff difference between alternative A and 0, and these are difference between transition probabilities. Okay, you have the definition. Okay, then we have this expression, and now I'm going to do this telescoping as Bob described. I'm going to do basically the same for this value V0. Okay, and we know that value V0 is the current payoff of today of choosing alternative 0 plus next period expected now at period t plus 2 value multiplied by the transition or integrated over the distribution of xt plus 2 if alternative 0 is chosen today. Okay, and then we have that now we have two terms. Okay, well, we have the value, the payoff difference today, this expression, okay, and now the value at period t plus 2, okay? And we have, and I'm going to do it only once, this telescoping, okay? And I'm going to do it only once because I'm going to consider that the class of model that I'm going to define, it can be defined more broadly, but I'm going to present the Euler operator only for models that satisfy the two-period finite dependence. Okay. Okay. And basically, what I'm going to say that now under two-period finite dependence, as Bob has shown, this term will be 0. And basically, we are going to have this mapping that relates value difference here into value difference, and that is going to be the Euler mapping. Okay, this particular part of the picture. Okay. Okay, then let me consider the definition here that Bob has presented several times, that let me reiterate here the definition of, in this case, of two-period finite dependence. To make this definition, let me consider this two-period forward transition probability. What this transition probability means. Given that we are at the state xt today, at period t, what is the distribution of x 2 periods ahead, given that we choose an alternative A at period t and some other arbitrary choice alternative at period t plus. Okay? Then this, by definition, and our Markov assumption, is a convolution of transition probabilities at period t and transition probabilities at period t plus. Okay? Then we say that we have a two-period finite finite dependence property if, and I'm going to consider a global definition, in contrast to Bob, that of course, in the case of Bob, we are interested in estimation. Then as long as we have enough that this finite dependence property applies for some state and some actions, that is fine. That is going to give us enough moment conditions such that we can identify our parameter. Here we are interested in the applying this for the solution of the model. Then we want this to apply more broadly, more globally, okay, in the model. Then we say that this model has a global finite, two-period finite dependence property if for every state xt, okay, we can, and any alternative, any arbitrary action at period t, okay, then basically it doesn't matter if you have chosen alternative A at period t or alternative 0, okay? There are always some actions that you can take such that the distribution of the state variables at period t plus 2 is the same under this path that under this path, okay? This is the finite dependence definition, the two-period finite dependence, okay? Fortunately, even this global definition of finite dependence applies to a very large class of models that we have in economics. I work in empirical I/O, okay? That perhaps we consider simpler models of the transition or the evolution of the endogenous state variables relative to labor, for instance. And in I/O, basically, every model of demand, inventory decision, investment decision, machine replacement, market entry and exit at different market satisfies this condition, okay? Very broad, okay? Very general type of model that, or property that we have in most of these models, okay? Okay, then under this condition, as I have mentioned before, basically this distribution, okay, is equals to 0, okay? Okay. This is basically, you can see that this is basically the difference in the transition, in the distribution of xt plus 1, if you have chosen alternative A at period t versus you have chosen alternative 0. Doesn't matter if you have chosen alternative A, implicitly in this F tilde, there is alternative 0. If after that you choose alternative 0, then or some other alternative, this could be 0, it could be other choice, then we have the same distribution of xt plus 2. And therefore, this term is equals to 0. And we can write basically this mapping in this way, where basically I have grouped in this function everything that is a primitive of the model, okay, or objects that are primitives of the model. The difference between current payoffs and next period payoffs under an arbitrary choice alternative, and with the difference of the transition probability between alternative A and alternative 0, okay? Then you can see here that the McFadden social surplus is a key object here, okay, for the properties of this book. But this is the mapping, and we have one of these equations for every choice alternative, state 1, okay, and of course for every state, okay. This is what we describe as the Euler operator, okay. Then in vector form, this describes a mapping from vector of value difference into value difference. And once we have value differences, we have choice probabilities, and we have the unconditional values, and we have everything. Then this defines a solution, a fixed point of this problem, defines a solution of the dynamic programming problem, okay? Then this is the key result, okay? Under two period finite dependence, okay? This, and for any distribution of epsilon, this applies to any continuous distribution of epsilon, not only for the logic model, okay? This is a property in general of this mapping when we have the social surplus function here, okay? This is a strong contraction mapping in the sense that it has a Lipschitz constant delta that is smaller than beta, okay? Smaller than the discount factor, okay? The proof that you can find in the paper in the notes in the material of the course applies, so an important ingredient of this is the Williams-Daly saccharine theorem. This Williams-Daly saccharine theorem says that the derivative of this surplus function with respect to values are the choice probabilities. Choice probabilities are between 0 and 1, and that is going to be an important property that is going to play an important role in this delta being strictly smaller than beta, okay? And in fact, the stronger contraction, basically how much delta is smaller than beta, basically what is the ratio between delta and beta. The smaller this ratio, basically the faster will be the convergence, the fixed point operation, iteration convergence of this mapping. It depends basically on the on the magnitude of the maximum of the probabilities here, this vector of probabilities. Okay, if we have a model where all the choice probabilities, set one, are close to zero, they are relatively small probabilities, then we are going to have a stronger contraction. Okay. What is the algorithm for the Euler iteration algorithm? Is just fixed point iteration in this Euler equation mapping. Very simple. You can see that basically in the logit model, you have this expression, you have the log of the sum of the exponential, you plug in some values here, you obtain the log of the sum of the exponential. This is a primitive, you obtain new values and so on. Okay. Then each iteration is as costly, or it has a small cost, as value function iterations. Okay. Basically, is linear. Basically, the main cost is the sum over all the states at period t+1. Okay. Basically, this increases linearly this computational cost with the number of states that we have here. Okay. There's linear cost of each iteration as value function iteration, but a contraction modulus that is substantially smaller than beta, then it converges substantially faster than a value function iteration. In all our experiments, close to quadratic convergence. Okay. And I think that this combination of these two properties definitely makes it a better algorithm than value function iteration. We are going to see that is also better than policy function iteration. Okay, because basically this cost is linear in X instead of cubic in X as policy function iteration. Okay. How much time do we have? Okay, this is a little bit a digression and is not so important, but let me make this digression. Okay, and it's why the name of Euler mapping? Okay, and the reason is that there is a clear connection between this operator that I have just described and the Euler equations that we have in continuous choice dynamic decision model. Okay. And let me remind you about these Euler equations in continuous choice dynamic decision. Okay, and let's consider now basically the same notation as before, but now A is a continuous variable. Okay, this can be extended to multiple continuous variables. Let me do it with one continuous variable. Okay, and let me distinguish two different state variables in the vector S. Okay. C that are exogenous state variables. They follow a stochastic process that do not depend on the action, and K that is an endogenous state variable. Again, let me consider only one endogenous state variable. Okay, this is important. Okay, we can similarly as the restriction of the finite dependence property that we needed to derive this Euler mapping that I have obtained before. For the derivation of the Euler equations in dynamic decision models, we need also to impose some restrictions on the transition rule or the transition probabilities of the state variable. Okay, let me consider this transition. It can be a little bit generalized. It is a little bit more general than this, but let me consider this transition. Basically, the transition rule of the endogenous state variable, the capital stock, if you want, at previous period, is a function, a deterministic function of the action today and the state today, and then an additive, and this is important, an additive innovation, okay, in this rule, okay? Then this is the Bellman equation, as before, okay? As usual, okay? What is an Euler equation? An Euler equation, when we are using continuous choice decision model, is a combination of two marginal conditions, okay? What we call the first order condition of optimality and the envelope condition. And we can combine two conditions to eliminate marginal values, to eliminate everything similarly as in finite dependence, we have been able to eliminate basically the expected value from period t plus 2 and to the future, okay? We have been able to use the finite dependence property to get rid of that additional continuation value. With the Euler equation, we will be able to do basically the same. We are going to be able to eliminate basically the marginal value from period t plus 2 to the 5, okay? Then what is the first condition? Is just basically applying the derivative of this intertemporal value function with respect to the action A should be equals to 0, okay? At the optimal choice, okay? And that's what we have here, okay? This derivative with respect to the action, the current payoff, then derivative of the value function with respect to the endogenous state times the derivative of this endogenous state with respect to A, that according to our transition rule is the derivative of F with respect to A. This should be equals to 0, okay? And then we have the envelope condition. The envelope condition says that the derivative of the left-hand side should be equals to the derivative of the right-hand side with respect to S, okay? And that can be written with respect to the endogenous state value, with respect to K. And we have this expression, okay? Then basically what we would like to do in this expression is to get rid, of course, let's try to construct moment conditions from this equation. Well, we need to solve the model because we don't know these marginal values, okay? Then the idea of the Euler equation is by combining these two equations, notice that we have marginal values here, or expected marginal value here, expected marginal values here. We can combine the two equations such that we can get rid of this guy and write an equation that depends only on primitives, on marginal profits with respect to the decision variable and with respect to the state value. And this in this model, this is the expression of this Euler equation. You can see that in both marginal profits today, marginal profits tomorrow, and some basically derivative of the transition rule with the state and with respect to the decision, okay? Here and here, okay? Okay. This is just the classical example of the consumption model. Let me skip it, okay? Then what I'm going to show you, or at least I'm going to sketch, is that the Euler operator that I have described before, I have derived before for the discrete choice, can be also obtained by constructing a continuous version of a dynamic discrete choice model. And how does this continuous version work? It's not an approximation, or does not involve any additional assumption. It's just a representation result. We can represent our discrete choice model where agents are taking discrete actions as using a model as if agents were choosing choice probabilities. And choice probabilities are continuous objects, okay? And basically, that's the idea. Let's consider, okay, that at every period t, what an individual chooses is a vector of choice probabilities for each action. Of course, choice probability that should sum to 1, okay? Then this is the decision of an individual at period, okay? Apparently, of course, we are making the problem apparently much more complicated because we are going from one single discrete action to a vector of many continuous variables, okay? Then given this choice, let me define now a version of the transition probabilities where instead of having the action conditioning on today's state and today's action, we are conditioning on today's choice of the choice probability, okay? And basically, this is the integration of our original primitive that is the transition probabilities conditional on an action over the choice probabilities. And basically, what this transition probability tell us is that suppose that we don't know what is the action that an agent has taken, but we know which are the choice probabilities of taking different actions. Then what is the transition, the probability of going to xt to xt plus 1, given that the individual is chosen action according to this choice probability? Okay? That's what this transition probability tells. Similarly, we can also obtain what is the expected payoff if the individual behaves by choosing this, by using these choice probabilities. We don't know what action the individual takes, but suppose that we know that it's going to choose according to these choice probabilities. What is the expected profit of behaving according to these choice probabilities? Okay? Then now, given these two definitions, okay, these transition probabilities and these payoffs, we can now define a dynamic decision problem, this dynamic decision problem, where the payoffs are these payoffs that depends on choice probabilities, and the transition probabilities are these that depends also on choice probabilities. And now we have a vector of value function that is basically the standard vector of values that solves this Bellman equation, okay? Well, it turns out that the solution of this dynamic programming problem give us exactly, of course, there is a unique solution because it's a standard Bellman equation, okay? The solution, the choice probabilities that we are going to get that solve this Bellman equation are exactly the same choice probabilities that solve our original dynamic programming problem with discrete choice. Okay. Okay. And then let me conclude this digression with this equivalent result. Then we can, if we have the finite dependence property, we can always define the following constraint optimization problem. Okay. Let's consider now that an individual can choose choice probabilities at period t and at period t plus 1 to maximize the profit at period, the payoff at period t and the expected payoff at period t plus 1. Okay, that's what this is. Under the constraint that these choice probabilities should be such that the distribution of the state variables at period t plus 2 should be the same, okay? Should be fixed, basically, okay? Any combination of choice probabilities at period t and period t plus 1 in this problem should give us the same distribution of transition probabilities at period. This constraint optimization problem, okay, is an alternative way of obtaining Euler equations to the one that I have described here. And this Euler equation can be obtained also using that type of Lagrange problem in general, okay? Well, it turns out that for this model, okay, if we solve this constraint optimization problem, we are going to get Euler equation in terms of choice probabilities at period t and choice probabilities at period t plus 1, and payoffs at period t and payoffs at period t plus 1, which are exactly the Euler operator that I have obtained. Okay? And that's why the name of Euler operator to that operator that I have described before in terms of basically using value difference. Okay? Okay. Numerical examples. Let me present some numerical examples illustrating that the computational advantages of this method. Okay. Okay, we consider a model of market entry and exit in a market where the profit, the choice can be 0 or 1. 0 means that the firm is not in the market. 1 means that the firm is in the market. The profit of not being in the market is normalized to 0. Okay. The profit of being in the market has 3 components: a variable profit, a fixed cost, and an entry cost. This entry cost is, I have changed, unfortunately, the notation here. I'm using D now instead of A, okay? Then this entry cost should be paid only if the firm was not active at previous period in the market. Only if dt minus 1 is equals to 0, okay? If the firm was active in the market at previous period, if this is equals to 1, 1 minus 1 is 0, this whole term is 0, okay? Well, here we call variable profit to a particular function that depends on these two state variables, C1, C2, and this exponential of omega that we interpreted as something like the total factor productivity of the firm. There is a fixed cost that depends also on these other state variables. All these C's and this omega are exogenous state variables. Then there is a state variable, exogenous state variable that affect the entry cost, and there is other exogenous state variables that affect that. Then we have in total 5 exogenous state variables, the 4 C's and the omega. And we have, in addition, also the endogenous state variable that can take two values, 0 or 1. Okay? And we are trying to consider a high dimension state space, to consider something a little bit challenging computationally challenging in the context of this simple entry and exit mode. Okay? These are just the difference parameters in the specification. All this, the C's follows an autoregressive of order 1. The omega also follows an autoregressive of order 1. The discount factor is 0.95. And we run experiments under 2 different values of the persistence in these autoregressive models. We consider one Monte Carlo with very low persistence and other Monte Carlo with very high persistence. Okay? Basically, as measured by the correlation between the exogenous variables between period t and period t minus. Okay? Not all the state. Yes, I think that omega. Okay, but I think that all the state values. Okay, this is going to be important for the performance of some of the methods. Some of the methods take longer if to converge if the stochastic process of the state variables present a lot of persistence. Okay, in some sense, it's like the beta parameter. Okay, a lot of persistence in the exogenous state variables is similar to having a beta close to 1. Okay. Then this is a comparison of the degree of contraction of 3 operators: our Euler equation operator, the value function iterator, and other operator that is called the relative value function operator, that under some conditions is known to have better convergence properties than value function iterator. What is relative value function iterator? Just take one state, okay, and define a Bellman equation where basically we consider the object of the Bellman equation in the left-hand side is the vector of values minus the value in one single state, okay? As simple as that. And then in the right-hand side, you can do exactly the same. You can basically consider the value, the difference between the vector of values and the value of one state. Well, it turns out that this very simple modification can have important implications in terms of the convergence properties of value function. Okay? Then this is the dimension of the state space, okay? And this is the degree of contraction. I'm not going to enter in the detail, but given basically the simulation, we can get basically the Lipschitz constant of each of these mappings, okay? The closer to 0, the fastest is the convergence, okay? This is for, low persistent, high persistent, okay? We can see that the value function iteration always, and this is not fixed, this is obtained basically numerically, but is exactly equals to beta, as it should be, okay? The 0.95. The Euler equation has a much smaller contraction, okay? And it's not Lipschitz constant or modulus of the contraction, okay? and it's not so different for the low persistent and the high persistent. Relative value function iteration has a substantially smaller modulus when we have low persistence, but as soon as we go to high persistence, okay, we see that is not different to value function iteration, while our Euler equation mapping operator still has very good Lipschitz constant that implies very fast convergence. Okay. Here we are comparing Euler equation, policy function iteration, value function iteration, and relative value function iteration. Here I'm reporting the number of iterations up to convergence and the time per iteration. In terms of the number of iterations, you can see that both Euler equation, policy function iteration, and relative value function iteration, typically the number of iterations that we need up to convergence does not depend very much on the state of the number of state values, okay? Which is very well known, was very well known for policy function and relative value function iteration. We didn't know if that was going to happen for the Euler equation operator, but you can see that this is also, we have also results that I'm going to present later, we have also for 1 million now, okay? Okay, then that's good. We don't need additional iterations when we increase this dimension of the state space. That is not the case for value function iteration. This is also a very well-known result, but value function iteration, the larger is the state space, the more iterations you need for convergence. And you need also, you can see also here the large modulus very close to 1. Basically, we need many more value function iterations to convergence than Euler equation iterations, okay? Now, in terms of the cost per iteration, you can see also that, in fact, our approach, okay, implies a slightly different, slightly small, okay, a cost per iteration than value function iteration or relative value function iteration, okay? You can see that for policy function iteration, this increases very fast as we increase the state space. And eventually, policy function iteration becomes basically impractical, okay, for large state spaces, okay? Okay, this is in terms of total time. Let me focus here in the time ratios, okay? This is the ratio in terms of total time, work clock time up to convergence. This is normalized relative to the Euler equation algorithm. You can see that for 200,000 states, that is relatively modest for some applications, okay? The cost of policy function is more than 3,000 times the cost of Euler equation, okay? But you can see also that value function iteration and relative value function iteration also imply. And this is for the low persistence. This is the best case scenario for the relative value function. If we go to the high persistent specification, you can see that now relative value function iteration, the cost is more than 40 times larger than the Euler equation. Okay. Then the method works pretty well compared to the traditional or standard method for solution. Okay. Let me describe here something that is relevant for estimation. Okay, what is what we do in this other, please? Yes, there are theoretical results for that. Basically, the relative value function iteration Lipschitz constant or contraction modulus depends not only on beta, or is the product between beta and an expression basically that depends on the eigenvalues, or the maximum eigenvalue of a matrix that depends on the transition matrix, basically, of the exogenous state value. Okay. Then if you have very high persistence, that maximum eigenvalue is going to be very close to it. Okay. That is not the case for Euler equation. Basically, as I have described before, here basically is not the model, is not basically the maximum eigenvalue of that transition matrix. It has to do with the choice probabilities. Okay, is the magnitude of this choice probabilities what is making this delta smaller. That the finite dependence property applies for multiple choices, or for multiple baseline choices. Here I have considered that this applies for the baseline of A equals to 0. And then basically the choice probability that we are not including here is the choice probability of A equals to 0. But if you have a choice of which baseline choice to use to construct your Euler equation mapping, choose the action with the highest probability, because that is going to leave here probabilities, smaller probabilities, that is going to give us a stronger contraction. Okay. Yeah. And if yeah. Okay. And let me conclude with this. What we do in this exercise? We have generated data using the DGPs with 1 million states, okay? And then we consider, okay, and we have considered a counterfactual experiment, okay? We have estimated the model, and then let's consider a counterfactual experiment where we increase the entry cost, okay? And let's solve our model, okay, to obtain basically these counterfactual choice probabilities under the counterfactual experiment, okay? And then what we consider is that suppose that the researcher has a limited budget, okay, for computational costs that it can afford, okay? There is a limited amount of time that he can spend by constructing this counterfactual, okay? We are going to the job market. We cannot spend. We are in October, okay? We are running our counterfactual experiments in October. You will see this is not unrealistic, okay? It's not my advice, but these things happen. And then we have limited amount of time to implement, okay? Then these are the true policy effects if we solve our model with our true 1 million states, okay? And these are basically the estimates that we will get, okay? Or these are the root mean square error, because this is a Monte Carlo experiment with multiple samples, okay? The root mean square error relative to the true value that we get with the different methods, where all the methods are subject to the same budget constraint of time, okay? That means that because some methods take longer than the others, the researcher will have to discretize more or less, okay, depending on the method. With policy function iteration, the researcher has to discretize a lot. Similarly, with value function iteration, with Euler equation operator, we can get closer to the true 1 million states, okay? Then basically you can see that this matters also for the quality of our estimates of the true counterfactual experiment, okay? It's not just computational cost per se, but at the end computational cost, we have limited time, okay? And this is the type of decision that we make as researchers. How long does it take to run these experiments with 1 million, 1 week. Okay, let's consider more like 10,000 or 100,000. Okay, because it takes us 2 days. Okay, 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 please. Because Williams daily Zachary theorem. Okay, you will need to see the proof that is in the paper in the notes. Okay, but notice that basically well, the F tilde does not depend on the choice probabilities. This is conditional on the choices. This is going to play a role, but it's going to play the same role in the different methods, basically, in value function iteration and in relative value function. The difference is that the derivative that here we are going to have basically this term in our contraction in the modulus. Basically, the choice probability is going to play a role in how strong is this contraction. Okay, which is not the case in the other. More questions? Okay, that's it. Thank you.